Today we're going to explore our next application of group theory, which is in determining the vibrational modes of a molecule. And it's actually easier to start with what I'm going to call a scavenger hunt approach to determining our vibrational modes. So let's say that we're in the lab and I tell you that we had made the facial isomer, right, the FAC isomer of a metal complex that had 3 carbonyl ligands and 3 chlorides. And so if we're going to draw out this, right, I'm using a generic metal in this case, right, but it could be something like cobalt. So let's go ahead and just slap cobalt on there just for fun. So let's imagine that we made this facial isomer of this cobalt carbonyl complex. So we might go ahead and start to draw this out. So we could see our cobalt center. We see it at 6 coordinate, right? So this should fit our nice octahedral kind of bonding pattern that we're used to seeing. Right, that facial isomer means that all 3 of those cobalts are on one face of that octahedron, or they make up the 3 different points of that face of the octahedron. And then I'm left with my 3 chloride ligands. Now, if we were in the lab and you had made this complex, the next question would be, right, how would you prove that this is the complex that you made? If this was a laboratory setting, maybe you made the meridional isomer. So the question remains, right, how can we confirm this structure? Right, confirm or validate this structure. And if we're looking here, we see that there are no proton signals, right? There's no hydrogens here. So a proton NMR wouldn't be very helpful. And if we look at our carbonyls, we might think of carbon NMR, right? And we could see some carbon NMR signals. But if this is a high spin complex, right, we would have a paramagnetic complex, which would not exhibit, or which might interfere, I should say, with our collection of any kind of NMR spectral data. If we grew a crystal, right, a crystal structure would be great in helping us determine this structure about our cobalt. But what is something that we could do in the lab that might help us understand this? Well, if we go back to our organic chemistry toolbox, one of the strong tools that we had in investigating the structure of carbonyls was IR spectroscopy. Right? IR spectroscopy would be a good tool here. Because, again, I have 3 of these carbonyls. And so I might be able to connect, right, these signals in the IR spectra with this particular cobalt complex. So let's say we go over to the IR, we gather our scan, we're looking for our carbonyl peaks, and lo and behold, what do we find? But 2 IR signals. Right? How do we end up with 2? So far, we can see that this is the carbonyl complex. I should have 3 carbonyls. So it makes sense maybe if each of them had their own stretching frequency. Or maybe if they are all working together, maybe they should have 1 stretching frequency. But how do we end up with 2 IR signals? Well, what we need to dive into in order to solve this mystery is actually group theory. So I'm going to redraw my structure here because it's going to make our life easier, right? So I'm just going to kind of say I'm redrawing our complex just so we can see it a little bit easier here. And what I'm going to do is I'm going to look down my principal rotation axis. And so this here is a C3 molecule. We would want to go through and assign our point group here. So we have a C3 rotation. We do not have any perpendicular C2s. That means that we are in our capital C point groups. We can see here that there is no horizontal mirror plane, but there is a vertical mirror plane, right? So in assigning our point group here, this is going to be a C3V complex, right? So we want to get back in the habit of assigning our point groups. And so I'm going to draw my molecule again as if I'm looking straight down that principal rotation axis. It'll make our life a little bit easier for this next step here, right? So I have my cobalt. I have a carbonyl, carbonyl, and my carbonyl. I have my chlorides pointed away from me. This is still an octahedral drawing that I have, but I have now just drawn it to where I'm looking down the face of the molecule that contains my principal rotation axis. So if you need to kind of confirm this, take a minute, build a 3D model of our octahedral structures, maybe even go to Otterbein and look up an octahedral complex and just see how I can convert between these two pictures. Because again, the spatial relationship, rotating and think about molecules in 3 dimensions is a really important skill in our class, and it takes some practice. And by drawing our molecule in this way, it actually makes it a little bit easier to highlight our carbonyls themselves. So I'm going to just redraw these so I can include their bonds. So I'm just kind of moving them around, and I'm going to color code them a little bit so they stand out better for us. So here, what we're looking at is our bond that is stretching for each of these carbonyls. So when we're looking at an IR spectra, what we are seeing is actually bond vibrations, right? The vibrational modes for individual bonds within our chemical structure. And as they stretch, if they cause a polarization of that bond, then we can see a signal in the IR. So what we're looking at when we look at an IR spectrum and we're looking at a carbonyl stretch is we're actually looking, right, at the stretch for each one of these. And currently, I'm only going to be drawing them along the bonding axis, as if these carbonyls are springs moving back and forth. And so the way that we're going to approach this is, again, using our group theory tools. We're going to do a very similar process to what we did when we looked for our molecular orbitals before. So that means we're going to need our character table, we're going to need this drawing, and we're going to create a reducible representation that represents the molecular motion along these axes. So again, like I said, we're going to need our character table. So make sure that you look that up. And so we have our compound, which I will paste back over here so we have it in front of us. As I said before, right, this is a C3V complex. So if we look up our character table, we can see that it has 3 different classes of symmetry operations. So it has the identity, it has 2 C3s, and it has 3 sigma Vs, right? So this is our character table that we're looking at. We can fill in our lines. So we have an A1, an A2, and an E. So we have our spherically symmetric case, right, where everything is a 1, A2 is 1, 1, minus 1, and our E is a 2, minus 1, 0. So now we have our character table. And so just like last time, what we need to do now is we're going to create a reducible representation, right, for my 3 carbonyls. So I'm just going to call this big gamma 3CO because I'm describing this bond stretch that's occurring along these carbonyls themselves. And we're going to use essentially the same tool set that we developed in our last class. And what I'm going to do is I'm going to look at each one of these stretches, right? And I'm just going to draw them almost like a vector, right? I'm going to say, when they stretch out along this direction, does it create a net polarization, right? We don't have to really dig into what that means just yet. But what I'm doing now is I'm going to use group theory to analyze these 3 green arrows. And I'm going to do it in the same way that we looked at our molecular orbitals in our last video or in our last class. So that means that if the arrow flips, this would be a -1 for my reducible representation. If the atom moves, right, or ends up in a different location than where it began, we're going to get a 0 for each one of these arrows. And lastly, if the arrow stays in place, that gets a +1. So these are essentially the same kind of rules that we use for molecular orbitals, but now instead of looking at orbitals, we're just looking at these arrows for these bond vibrations. And so under the identity, right, when we do our symmetry operation and everything stays in place, I have 3 arrows that have not moved, right? They're in the same location that they began. So my reducible representation would get a 3. I move on and I look at my C3 rotations, and I see that when I rotate and do my C3 molecule all of my atoms end up moving, right? They are no longer in the same place as where they began. So when I do my C3 operation, right, this gets a 0 because all three of these green arrows have moved from their original location. When I look at my sigma V's, right, the sigma V's contain a single carbonyl inside that mirror plane. And so because of this, right, two of my arrows end up moving, and one of my arrows is contained within the sigma V. So that means that I'm going to give a 1 to my sigma V set here. So this reducible representation, this big gamma that I've derived, just describes the molecular motion of my carbonyls under this point group. So I have this reducible representation that represents the different ways that these arrows, right, these vectors essentially can interchange within this point group. So what do I do now? Well, if I have a reducible representation that I've now generated, my next step is going to be to break this down into the contained irreducible representations. So let's take our table here. We're going to take this with us. And what we need to do is we're going to test one by one our irreducible representations to see what is contained in our reducible representation. So the way we could think about this, right, is that gamma 3CO, right, we're trying to solve what does this contain? What is it equal to? And so we can go through our same method as last time. So we can count our A1s that are contained, and we take our class order, right? So for the identity, it would be 1. If we're checking for A1, we would multiply the character of our character table times the character of our reducible representation, right? So that means that we end up with our 1 times 3. And we're going to continue down the line. So that means we would take 2 times 1 times 0. We're just going to add all of these up. Right? When we take all of these, then we need to multiply them, right, by 1 over the order, which in this case is 6. And this is the total number of symmetry operations for our given point group. So what we see is that this is 6 times 1/6, which means there is one A1 contained, right, in our gamma. So we're going to continue this process for A2 and E. So for A2, right, we're essentially going to be looking at just a different set of characters here on our character table as we evaluate our irreducible representations. So we can see here that we have 1 times 3 again. Here we have 2 times 1 times 0. And our last set is 3 times -1 times 1. All times 1 over 6. So 0 times 1 over 6. So there are no A2s in our reducible representation, right? Our 3CO, our big gamma 3CO. So let's check out our final irreducible representation here. So this is going to be E. So let's test to see how many E's are contained. And so that means that we, again, have our nice brackets. We have now 1 times 2 times 3 plus 2 times -1 times 0, right? That's a -1. It's not like I spaced out on writing a 4, which is kind of what it looked like there for a second. And lastly, I have 3 times 0 times 1. So this is 6 times 1/6 again. So that means there is one E contained inside our gamma. So now we can go up and we can fill in this question mark that we have, right? What is this reducible representation contain? So it is equal to A1 and E. So we now have two irreducible representations that are contained within our reducible representation. So what do we do with this, right? This is still all this group theory business that we're digging into, But how do I interpret this result, right? What do I do with this now that I have it? So what we have to do is we have to figure out, what does this actually mean in terms of vibrational spectroscopy, right? So these represent the molecular motion, the molecular vibrations of my three carbonyls. So what does this mean? Well, what we need to do is we need to look at the rest of our character table. So we have this big gammas, A1 and E. And what we have to do is we need to actually look at our coordinates, right? So the next line over, which we can sometimes derive, and sometimes it's a little bit more complicated, right? So we're not going to be able to derive it directly. And what we see when we look in our coordinates file is that the spherically symmetric case, A1, has our coordinate Z. We can see that there is RZ represented by A2. We're going to use this in our next class. We don't need RZ today. But when we look at E, this is X and Y. And again, we have Rx and Ry that are down here. Now, these big capital R's, what this means is this matches the symmetry of a rotation about that particular axis. Again, we will get into this in our next class. All we care about right now is actually X, Y, and Z. So if we have, right, if we have an axis for an irreducible representation, that represents a IR active mode. Essentially what this means is that underneath that particular symmetry, or underneath that particular irreducible representation, there's a net polarization that occurs across our molecule that would result in an IR signal. The way that that again works is just if we can see, right, that we have an axis such as Z or X and Y, that particular mode, right, being A1 and E, are IR active, meaning they would have an IR signal. If we were looking at the C3V point group, right, if I had any A2 signals, right, A2, there's no axis, right? That means that these would be IR silent modes, meaning we would not expect to see a signal here. So if we look at our big gamma that we derived that contains A1 and E, right, these are both active. That means that we would expect to see two signals in the IR, which in fact we do, right? If we go back to that original slide, if we go back to the beginning of the video where I said, we go in the lab, we gather an IR spectrum, we would expect, and we see that there are two carbonyl stretches. Now we've used group theory to support that assignment, right? For our facial isomer, we would expect to see two signals in the IR. We're going to get a lot of practice with this. So this method allows us to look for individual types of stretches. So in this case, when we're looking at complexes that have lots of carbonyls on them, maybe even like your computational report, where everyone has at least a few carbonyls on their compounds, we can look for the number of vibrational modes that would be contained or present for a particular type of stretch, in this case, a carbonyl. So now what you should go and do while you're practicing and this is still fresh is to try, right, the same derivation, right? So try the derivation for the meridional isomer. Right? So go and try this right as you're practicing and see what you come up with. Would IR actually tell you the difference between a facial and meridional isomer using group theory? So, like I said, we're going to get some more practice with this on looking for individual stretching frequencies in our next class. Our next video is actually going to be focused on determining all of the vibrational modes for a given structure. So let's say that we weren't just looking to confirm our structure using a carbonyl peak, but what if we looked at the entirety of our IR spectrum? Could we actually determine each and every one of our signals on an IR spectrum using group theory? All right, thank you. Have a nice afternoon.